Okay, so let me give you a little bit of context. This isn't all in the main paper that I was going to talk about, but it's just important background knowledge. So Xilinx pioneered this for FPGAs, where they basically make their larger FPGAs out of multiple dice, and they do it. All the dice are identical. Okay, so if they want to make their larger chips are usually 3 to 4 of what they call these super logic regions. And you notice each of them is identical. So they make the same die 3 times. They stack them together. They've all got, they're column based. So a bunch of memories, bunch of DSP, bunch of logic, bunch of IOs. The IOs are in columns as well. And this is Vertex 7. So they put these together on a silicon interposer and they sell you a big die. Okay, so the advantages are you get better yield because you only need 1/3 of these things to work instead of an entire one. And for big dice, that is a big difference. It's not just the probability of a defect hitting this die is a lot lower for a big device. So you get much better yield by doing this. For example, when Xilinx first did this, which was at 28 nanometers, the biggest FPGA, the other thing it could do is they could make a bigger FPGA. So I guess it's 2 things. You yield bigger chips better. You also can make just an extra large chip because you're taking multiple pieces of silicon and sticking them together. So at 28 nanometers where they first did this, they made a chip that was twice as big as the biggest monolithic chip that like Altera could make. And there's generally a market for the biggest FPGA you can make. People who are like prototyping ASICs, for example, they usually just want to buy the biggest chip. They almost don't care about price. I mean, maybe they care a bit, but they're pretty price insensitive, and the FPGA companies take advantage of that. This is not as big a deal, but you can save some mask costs. Let's see the floating meeting controls. Yeah, screw that. So you can make one mask, and now you can. Xilinx did this at 28 nanometers. They made one chip where they repeated this 3 times, and another chip where they repeated it 4. And okay, they only had to tape out 1 thing instead of 2, so that helps a bit. But it has to be better. If this is as hard to use, like if you got as constrained an interconnect between these as just putting it on a board, then this is pointless because I can always just buy multiple chips and stick them on a board. So it's got to beat that. But Xilinx has been using this now for quite a few generations. Everything from Vertex 7, which was 28 nanometers, down to their, I think Versal 2 is like, I forget if it's 7 nanometers or 5, but all the way through that they've stuck with this, so they like it. This is kind of a view of what it looks like if you zoom in more. It's again a Xilinx picture. So they have these pieces of silicon that are the FPGA devices, and then they have a silicon interposer that is a passive piece of silicon, so no transistors, just wires, and they have micro bumps connecting you. And they get a lot of wiring between these things. And then you have to have through silicon vias to get up to to get power and ground, and to get signals from the IOs out to the package, you have to have through silicon vias. So there are some pretty big vias that are etched right through the silicon of this bottom die, which is the interposer. And this is what that looks like in more detail. So you've got your interposer here. This is your package. A package is like basically the same technology as a circuit board, but a bit higher quality. An interposer is silicon technology, so you can get a much higher metal density. You can see the through silicon vias. So you got solder bumps going to the interposer bottom, through silicon vias going up to where the FPGA is. All right, and then also you have these micro bumps that are allowing the FPGA to get to the interposer wiring and make connections like across this gap. Hopefully that makes sense, gives you an idea of what it looks like. Okay, so what's the cost? So you can't get as much wiring on the interposer. Like those micro bumps still are, depends on the technology, but they maybe got a 25 micron pitch. Even if you pull them back several millimeters from the edge, which is what Xilinx does, so they actually don't try to put all these micro bumps right at the edge. They'll go back several millimeters away from it and just cover it with micro bumps, all going down the silicon interposer wires. They can only get, in this Vertex 7 part, for example, they can get about 23% of the vertical wiring across. So they've got much narrower routing channels effectively when they cross the interposer, and there's an extra delay hit. And in this generation, that extra delay hit was about a nanosecond. So they're extra slow and extra scarce wires. And this is probably getting worse. I haven't looked at it for their most recent chips, but micro bumps haven't, they're scaling. They are getting smaller with process generations, but they don't appear to be scaling at the same speed as just regular wires. Might change with something called hybrid bond technology. Hybrid bond technology doesn't use solder bumps at all. And so if you had hybrid bond, usually that's done for like sort of 3D chips, right? But if you have hybrid bond to an interposer, then your density of that, which doesn't use solder bumps, it's like a fancy technique where the copper plus some special materials effectively just bonds to the copper of the interposer, like of the other chip. That can get you pitches down to 5, maybe even 2, maybe even the future 1 micron. So anyway, so I guess the summary though is you can't get everything across the interposer. Is that getting worse with process scaling? It was for a while, but maybe with hybrid bonds, hybrid bonding, that will no longer be true. Okay, so Xilinx did a pretty clever job of how they productized this, in my opinion. They didn't make end users think about this. Okay, so you've got really 4 pieces of silicon in this big chip, but they basically hid that. I mean, they told people that's how they did it. It's cool, but from an end user using Vivado, you didn't have to worry about it. So you could just write your HDL like you normally would, press the button, it'll just synthesize, place, and route. They could be using partitioning internally. They've never really said what they do, but it's hidden. Okay, so it's integrated into their placement engine, and you just don't really see it. When you took, if you took like a bunch of FPGA chips and put them on a board, and you said, let's use them as if they're one big chip, which is what ASIC prototyping does, you generally have nowhere near enough IOs, and you have to time domain multiplex the IOs. Okay, so you slow your system down, you take maybe get 10 IO cycles for every system cycle, and it's very visible. All right, like this is not like a hidden thing. Like the end user sees this, they know that the system's running slower, etc. So Xilinx didn't do any of that. So they're not time domain multiplexing across this boundary, etc. So in this paper, which is one that the paper I'm supposed to be reviewing today builds off of, myself and some former students took VPR and we modified it so we could say we've got cut lines where we're going across an interposer. So we gave it a few command line parameters. How many cut lines and how many wires get cut? So here, for example, said maybe 75% of the wires are cut. Okay, so the channels get narrower at these cut lines, and they also get slower. And we can specify that too. And then we made some enhancements to the CAD tool to try to optimize for that, and then ran a bunch of experiments. And this is probably the most important one. How many wires can we cut before it starts to really hurt? And basically, you can go to 80% of the wires, 75% of the wires before it starts to really hurt. Right? You start hitting a wall here, like the minimum channel width is going up. What that really means is I just need to keep. You cut 90% of the wires, you got to make the channels twice as wide, which effectively means you're now limited by the interposer. Like we can't really make up the problems elsewhere. So that was supposed to be basic background knowledge, some of which you guys will see if you took 1756, because these are still from some of my slides from that. Does this all look pretty clear? Any questions on that? Okay, sounds good.
Sorry,
Yeah.
I just have one small question. So for the chart that you showed, is placement also updated to be aware of these cut lines, or placement is just working?
Yeah, they are updated, and that's important. So I was going to show you a quick thing. This is now going to the first of the, I guess I gave you a quick overview of this paper. This is the paper that is the predecessor of the main one we want to talk about today. But I was going to quickly go through a few highlights from it. Okay, so let me just flip back to the start. Okay, so yes, this was done in VPR, but as those of you who were in the meeting with UCSD know, it was done in a branch of the VTR 7 release, so it's not in the current code base, so it'll be useful to get in. So let me just flip down and show you a few interesting pictures. Let's see. So first, how do we model this? I guess in a little more detail, the most important thing is to change the routing resource graph. So we built the regular routing resource graph in VPR. So you see there's this wire here going vertically. And then we basically applied these cut lines, this wire would actually be cut. You'd have a piece above, you'd have a piece below, and we put an extra interposer node in. Okay, so we did it with a post-processing pass, and we also gave this interposer wire like the appropriate delay. So for Mir, this was much easier, right? So I think something like this is probably the right way to do it if we bring it into VTR9. And now you wind up with a new RR graph. But we didn't have to rewrite the whole RR graph generator. We could do it with a post-processing step. Okay, so the placement cost in VTR was updated. So the basic placement cost is, we got a timing cost, and all we had to do for that was make sure that but basically the timing cost is take the criticality of a connection, so your estimate of whether it's going to limit your speed or not, and multiply it by the delay that you would expect for that connection in a netlist given the placement of its source and a sink. And all we had to do was update this delay function. So it now understood where the cut lines were and it had some extra delay in. And then the placement engine now understands that if it crosses a cut line, it's going to take an extra hit and delay. The next thing that we did, so that's just saying update the delay function. So some will be familiar with this too. The basic cost function for wiring in the placement is you estimate the amount of wiring by the span of the bounding box in the X direction and the Y direction for every net. This doesn't matter much, but we multiply by a small correction factor for nets that have lots of terminals. And we divide by the average amount of wiring in that direction over that, in that direction, right, per channel. So what we did, experimented with a few different things, but basically what worked best is we just kept that wiring term and we added in a cost to cross these cut lines. And the one that worked best was kind of interesting. Like one that you might think would work well would just be count how many cuts you crossed, right, and put a penalty in. And that did help, but it worked. The problem with that cost function is as you're moving things around, you can't tell if you're getting closer to not crossing the cut line anymore, right? You can tell if you crossed it or not. You've got a net that spans an interposer or not. I think I got a picture of this in the next slide. But you can't tell if I'm gradually moving terminals down and I'm getting close to being not cut anymore. So these kind of discontinuous cost functions can be harder to optimize because you have no guidance. So we did something a bit different. We took, are you crossing the interposer? Well, how many interposers do you cross for a net? Multiplied by the amount of bounding box that is on, I think we did a bad job of describing this when I read this again, but on the like on the shorter side, okay? So take basically, well, maybe it's better to show by a picture. So this blue net doesn't get any extra cost because it doesn't cross this interposer, which is the dashed line. The green net does get an extra cost because it crosses the interposer. And the dotted black one does get an extra cost because it crosses the interposer, but because its height is lower, it's only 3 high instead of 4, the cost is not as big because the formulation we used was bounding box height times number of interposers we crossed. We used height because all the interposers are like horizontal cuts. So this basically makes you, if you're not crossing the interposer, we don't care. If you are crossing the interposer, try to get short and fat, because maybe that'll lead to you not crossing it anymore. And actually now I remember, we found this height worked best. We also tried one where we took like, well, how much is on the other side of the interposer or the smallest side of the interposer? It didn't work quite as well. So we just went with this one. We never fully understood why, which is why the text just kind of states it. And so now I'm actually remembering, why did we just say that without giving more intuition? It's because that was a little bit confusing.
So sorry, for this one, the one end up applying is not saying how much it passes the cut line.
Yeah, it's not saying that. I believe that the equation we give there is actually correct. but I'm pretty sure we actually tried the other one, and it wasn't bad either, but it wasn't quite as good. So we went with this one, but we kind of went, the other one makes more sense. Now it's a while since I did this, so I also have to go back. You can actually find it on the wiki. So this is what's so good about the wiki, to make sure we did try the other one, right? And didn't just like kind of, somehow forget to try it. But yeah, the text is correct in what we do, but it's a little surprising in some ways. You would think keeping whatever, is the shorter side would be a little better, right?
So
It was interesting though. Like this behavior of like a 0-1 constraint can be a little bit harder to optimize. So finding ways to sort of make it a bit smoother is something I've run across multiple times.
so Vaughn,
So
just a
go
quick
ahead, Alex.
question. So what this paper was doing was it just treated the interposer as if it was one big FPGA, but there were these connections between the interposers which looked like slower routing connections between the two regions on the FPGA. Is that a
Yeah,
good summary of what this was doing?
yeah, that's exactly. It was still one big grid. The RR graph was different at the interfaces,
Hmm.
and we remembered where the cut lines were because that was helpful.
Gotcha. Super interesting.
Okay, so then let's see. I'm gonna scan down this. I'm not going to talk about, oh, this is the router. So we just had to make sure the router look ahead understood this too, right? So the router look ahead usually, well, at least at this time, just kind of said based on what kind of wire I am and how far I'm going, I can estimate what's going to happen in the future. We had to make it understand, well, think about how many cut lines you're going to cross. So the router look ahead needed an update too. And that's basically what this is. Okay, so
And the reason for that, Vaughn, is because of translational symmetry. It's the fact that the original router look-ahead assumes that going right by 50 tiles is always the same no matter where you are on the chip. But you're saying no, because of this interposer, going up on 50 tiles is going to change because of these cut lines.
yeah, that's exactly it. Yeah, the look
Interesting.
ahead to reduce data, assume translational invariance, and now that was broken. So in my mind, Amir, you're already locked in. So I don't know, but I mean, a nice way to do this. So we did it by just saying where are the cut lines and running code for that. Uh, it's kind of interesting. Could you like make a general solution where you actually figured out it's not translationally invariant and data reduced that?
Right.
Do you know what I mean? No, you don't have to. You could do exactly the same thing if you know where the interposer cut lines are. But there are other ways that FPGAs can have, I don't know, large blockages or weird processor complexes. Terra loves doing this, right? Like they stick a processor complex in the middle of like some spot. Like Matthew Hall, who did the H-pipe CNN accelerator, like found all the irregularities in the Stratix 10 fabric because you'd have readability and timing problems around them all. Um, so maybe you could actually make, if the lookup right now is built by code that is essentially searching the routing graph and doing data reduction techniques. So it's kind of interesting. Could you actually find these discontinuities without telling it in advance they exist and have it figure out, here's how much data I need to store so that I don't assume translational invariance. But I can't just make some giant like 15-dimensional table because it'll be the size of the world, right?
Right.
So those were like placement optimizations, and they work. So basically, if we cut 80% of the wires in an interposer boundary, which is roughly what Xilinx is doing, this saves you like a reasonable amount, 20% of your channel width by turning on these placement optimizations. If you don't cut much, then they don't gain as much because they're not as important. But this is kind of where commercial, well, Xilinx chips are anyway. Okay, so let's see. And what else was this? And same for circuit speed, it's also helpful. Okay, so it cut the circuit speed too, or helped the circuit speed, sorry. We also tried, and then we also tried partitioning. Okay, so when you have a really difficult constraint, if you can't get many signals across a certain boundary, that's what a partitioner is built to do, right? Cut a circuit into pieces with the minimum amount of crossing between them. So we incorporated partitioning in a couple different ways. So we could do it before packing, and then constrain the packer to it couldn't pack things from the same partition together. So if we had 4 sub-dice, we would cut into 4 pieces, and then the packer could be told, those are 4 separate problems, basically. Or we could just choose not to do that. We could also constrain the placement. So we could generate these partitions, and we could say, tell the placement engineer, well, you got to put each partition on a chip. You can only move within them, or we could not do that. And we could run the partitioner. If we're going to run constrained packing, we have to run the partitioner before packing, like on primitives. If we're going to constrain only placement, we could run it on the clustered netlist. If that makes sense. Okay, so what did we do here? So we found, we wanted to have heterogeneous balance constraints. So these different sub-dice have, some RAM in them, some logic blocks, some DSP, some I/O. So when you're partitioning, you have something called a balance constraint of how much stuff do you have to put in each of the partitions for it to be legal. And 2 leading partitioners are HMetis, which partitions hypergraphs, meaning that it's an actual netlist. You can have fan out, right? You have a source and multiple destinations, it's okay with that. But HMetis doesn't understand these heterogeneous balance constraints. It just understands you got to split this roughly in half, but it's like half, there's no notion of it's got different kinds of things. Metis is a graph partitioner, so it doesn't understand hyperedges. It has to just one source, one sink. So you have to split up. If you have a fan out 5 net, you have to split it into something like 5 edges. But it understands different heterogeneous balance constraints. You could have one for RAM types. It doesn't understand RAM, but you can basically say there are multiple types of nodes, and each of them has to be balanced within this much. So we used Metis so that we could use that heterogeneous balance constraint. And then we looked at, well, that means we have to take a hypergraph like this, right? So we go from A to both B and C, and we have to decide how to split it up. So we could split it up into, for example, a star model. From A, you go to B, and you also go to C. Or we could split it up into like a clique model, where you just connect all the terminals together with edges. And then you can also choose how much you weight these edges, right? So we have some edges, hyper edges that have just one fan out, and we have others that have more fan out. So how much should we weight these edges? Should they be different? And Metis understands edge weighting.
Vaughn, quick question. Sorry to pause you for a second. Normally when I see a star model, you usually create a fake node in the middle, and then you connect the source to the fake node, and then the fake node to everything else. Are you avoiding
so we didn't do that in this, and it probably wouldn't make, we didn't think it made sense here. When we say star model, in the star model, the start point is the driver, because it's a more physical model in a sense. Do you know what I mean?
Gotcha. Maybe it's something really in the AP.
That's actually an interesting thing if you're putting time, I guess when you're putting timing in, you're not making star nodes, right, in your analytic placer.
Let me think. No, I'm doing a clique basically. Or no, I'm doing exactly what you're doing. Never mind. I'm doing basically what you're doing.
So for timing, this definitely is I think makes a lot more sense.
Yeah.
For wiring, it also makes sense to me, but you could argue for
something to explore. Yeah.
Anyway, so this is the 2 models we did, the clique or the star. And star really is like just decomposed into a bunch of source sync connections. Let's see. And then we also looked at how much do we weight things. Okay, so if I got a net, so this is the summary of all those things. So I've got a hyperedge with n terminals. I could make that a clique, and that's going to give me n squared edges. And I could weight each of them with 1. That is disastrous in terms of cut size, like the number of things you're going to cut. And this is hypergraph cut size. So it means we don't use the actual graph. We go back to the hypergraph, so it's a fair comparison. So this is, if you think about this a bit, this sounds kind of stupid. It is stupid, okay? But we did it just to show stupid.
Cut size, do you mean like how many crossings?
How many crossings of the partition. And the cut size we're measuring on the hypergraph. So the original net list, not on the graph, because we measure on the graph, it's going to get really confusing. We just made different graphs for all these things. They're all going to have different cut sizes, but that doesn't really mean anything. Okay, so we knew this one was going to be dumb, we just did it to be sure. You could do a clique, so n squared edges, if you have n fan outs or n terminals on a hyper edge, but weight them all as 1 over n, or weight them as 1 over n squared. Or we could do the star, and we could weight every edge the same, or we could weight it as 1 over fan out, and that's the best. And what it's in a sense is intuitive. What that well, maybe couldn't have guessed it, but what this means is that every hyperedge has the same weight. Because if I have 3 fan outs and so I have 4 terminals, I get 3 edges and I weight them each as 1/4. It's pretty close to if I had 1 fan out and I weighted as 1/2, if that makes sense. So every hyperedge turns into n edges. They're all, or actually n minus 1 edges, and they're all weighted as 1 over n. So it means every hyperedge has about the same weight when we break it up. So it kind of makes sense, and it did give a much better cut size. We also thought, well, maybe what if you really focus on the low fan out nets, because those are often the ones that you can do a better job of grouping. So what about 1 over n squared to really focus on the low fan out nets? And that was a bad idea. So that's cut size. We also looked at, we take this, it was better to constrain packing. Okay, so the best partitioning flow was definitely to do it before packing. It was a bit helpful to constrain placement, but not as important. So it was kind of debatable, do you constrain placement or not, but it was important to constrain packing. And if we basically take these partitions and look at what did they do to our minimum channel width. Again, we find the best result happens with this star topology and 1 over n weighting. Does that make sense? Although it's not nearly as extreme. You can see the cut size difference is extreme. The difference in channel width is not as big.
Just to confirm, Vaughn, so that figure on the top right, is this constrained packing, constrained placement, or constrained packing with the placement optimizations that you showed in the previous section?
Yeah, I mean, all the placement optimizations are on. So those are on for everything, okay? And it's definitely constrained packing. I think for this one it's also constrained placement, but whether you constrained the placement or not didn't make that much difference.
Gotcha.
So, and that's actually what's shown here. So this is basically what channel width do I get across a bunch of circuits that are too small. So these are VTR designs. So by using Titan designs, which we couldn't do back then, you'd get much bigger designs. But basically, if you look at if you don't use partitioning, you get a certain channel width. If you partition and then constrain packing, you get a much better result. If you partition and only use it to constrain placement, it doesn't really help much. And if you partition and use it to constrain both packing and placement, it's the best for minimum channel width, but only a little bit better.
So the reason to pack the constrained packing is to just prevent 2 atoms that want to be in the same cluster together from crossing the partition line? Or
Yeah,
crossing the
yeah. If you just let things be packed first, then the partitioner, you've already messed up a bunch of stuff that the partitioner can't stop you from messing up. So I think it's
Interesting.
similar to some of the things Amir is finding. And I think we also did have unrelated logic clustering happening here. So this is probably would not be as strong in VTR9 because of the fact that the pack is probably smarter.
So good news is I do have the code for this. So the
Oh wait,
constraint packing, I have the code for that.
wait. So Vaughn, this had unrelated clustering turned
Oh,
on.
okay. Well, it was on by we didn't have, yes, I think the short answer is yes, because we didn't
Oh,
actually kind of separate that out until VTR8.
never mind. These
So,
results make total sense to me now.
yeah. So, anyway, I'm almost done with this one. Sorry, it's taking me a long time, but,
Good paper.
okay, so this is just summarizing what could you get from CAD flow improvements, and actually, this was an older work by us. Basically, it shows that the CAD flow improvements are better than the ones we had in our previous paper, and we can push the number of wires that are cut by the interposer boundary like pretty high before things start to fall apart. And let's see, there were actually a lot of results in here. So then we also looked at architecture things. So we looked at, okay, so these wires that go through the interposer, yeah, you're basically limited by these bump pitches. That's what's limiting how many wires you can get through that interposer. So we could make those wires a bit more usable by making them bidirectional, right? Have a tri-state buffer on both ends rather than the typical FPGA interconnect thing of you got a mux and you can't shut it off. So that's, if you got a check here, that's bidirectional. We also looked at, well, basically, could we put bigger muxes on the input to that wire, and could we make the output of that wire fan out to more muxes? And we give those maybe complicated names of fan in transfer and fan out transfer. If you did all those things, you could basically bring the minimum channel width down by, maybe 12%. Okay, so it is making your interposer wires more usable. It didn't have much impact on critical path delay. So brought it down a little bit. So it means the router's been pretty good at like taking the critical path and still putting it through a direct route. We couldn't make things much better. But we can make it easier to use these wires, and that does help routability. And let's see. And they kind of stack. There was, like the combination of making them bidirectional and making them easier to get to was better by quite a bit than either one of those by itself. It does kind of make sense. There's no real reason to believe that partitions should be balanced in terms of you're sending data down and somebody's sending the equal amount of data up. You can think of a lot of data paths where it might want to send data mostly in one direction. But I guess without increasing the mux sizes, we probably had trouble getting to those wires, so we didn't see the full benefit. And I think that might be about it. Yeah, so these are just more results. Oh, this last one's actually kind of interesting. So we also looked at, when you make a chip, if you want to fit the most number of chips onto a circular semiconductor wafer, it's a bit better to make them square. Okay, so most chips are at least somewhat square. If you can go to 2-to-1 aspect ratio, it's not too bad. But people try not to make really long and skinny chips because they don't fit as well on a wafer. And what we've been doing in the previous stuff was we're basically making essentially a square total system, which means that the individual dice are actually a bit short and fat. So we also did, well, what if we made the individual dice square, and then the interposer is going to wind up being tall and skinny? And it's reasonably catastrophic. So you do not want to do that. Where was it? I guess it's in one of these result tables, but it was a lot worse. And it kind of makes sense. The reason it makes sense is if we're cutting in this direction, you kind of are getting a lot of vertical channels, and that's kind of helping you. If you stack things this way, you don't have as many vertical channels, but you still have a lot of signals that want to travel far. So it's not a good idea, right? You should actually push your dice to be kind of as squished out as you can if you're going to do interposers in this direction. And yeah, that's it for that.
Well, it kind of makes sense because it's like volume over perimeter. You want to not minimize, the volume of those die is going to be how many signals can be in there or potentially want to cross. And your perimeter of those die is basically how much space can you cross. It's kind of cool.
Yeah. So I'm going to pause there because I went through that. Maybe, I don't know, is that too fast, too slow, or what? Don't worry, it won't hurt my feelings. Okay, so I'm probably not going to get through all of these papers today. But let me go on to the next one. This one I probably can get through. It depends on what level of detail you want me to go through. Okay, so this is a paper from Andrew Kahn's group in UCSD, co-authored with Intel. And basically, the reason I went through that previous paper is they really took that work and they updated it with a new partitioner. Okay, so that's really what this paper is all about. And so let's see what they did that's different. Their partitioner is quite interesting, okay? And that's why I went and I read the paper on their partitioner, because it's got a lot of new, basically their partitioner is called Triton Part, okay? So it's now a competitor to Metis and HMetis, which have been the dominant partitioning tools for a long time. And their Triton part has a bunch of interesting algorithmic things in it that are in yet another paper. So we're not going to get through all that. But what they did is they basically took the results from that previous paper and said it's important to pack, like to partition before packing. But there are things that you really shouldn't cut, like carry chains and so on. And we've gotten better at having benchmarks with all these complicated things in them since that VTR7 paper. So they take the pre-packer from VTR and have it actually output what it's done, basically, right? So the same kinds of things that you get, Alex, where you keep those together in your AP net list, they also grab those pre-packed LUTs plus flip-flops and carry chains, and they'll keep those together. This one, I think I have to like wait till we get there. Their partitioning algorithm is complicated. And these are kind of two enhancements to their partitioning algorithm on top of their existing partitioning algorithm, which itself is very complicated. But it's interesting. So I think, yeah, so what they find is overall it works better. They get, I think these are up to numbers. So their up to numbers are like 14% improvement in wire length and 23% at Fmax. Their averages are around half of that, maybe somewhat less than half of that, half or a third of that, by upgrading the partitioner, right? So same flow, except they're not going to use HMetis and Metis. They're going to use their new partitioner. So that's kind of the bottom line. Their ultimate average gains are on the order of 3 to 5%, but there's like kind of no cost. It's just like use this better partitioner, and it'll work better than when you use these partitioners.
Just in the last paper you talked about, you said HMetis it couldn't it could handle hypernets, but not a hybrid, not different types of blocks.
Yeah, heterogeneous balance constraint. Yeah.
And Metis could do that, but it wasn't able to do hypernets. Is this one able to do both, or is it which one is it more closely related to?
It can do both.
Gotcha.
Yeah, so Triton part is actually quite full featured, and it's part of, so Andrew Kahn is a well-known person in the CAD literature, and he did a lot of the stuff for Open Road. Okay, so he's big into open source CAD tools as well. So I think Triton part is open source, and probably like my guess would be like well-engineered open source, right? Because he's trying to build tools. There's kind of two levels of open source. Another academic that you might have been there. I think Hong was at FPT one year where an academic said there's open source and source open. Source open is I stuck it on GitHub, right? There's no tests. There's no tests. There's no documentation. There might be a comment in there. Good luck, right? Your probability of making this work is almost zero. And then there's open source where it's properly engineered and has tests and stuff. And I haven't looked at the Triton part source, but my guess is it's the open source, well engineered type. Okay, so let's see. So I kind of this is like a summary of the paper I just told you about, right? So you already know this. We put in these horizontal cut lines, modify the routing resource graph, adapt the placer. So they basically take that code. They're using all that stuff. But they're changing the partitioner. So this shows their flow, right? So they run through VTR's pre-packing. They send that off to their partitioner. It'll respect the pre-packing, generate partitions. They bring those in to guide the packer. The packer gives them a clustered net list, and they place that, and they make the placement obey the partitions as well. So they don't want it, it's allowed to move things within it, but they don't want it messing up. I've got to read really carefully, I guess, but from this arrow, I'm pretty sure they're making it respect the placement constraints or the partitioning constraints. Okay, so this gets into their partitioner, which is interesting. So, and actually, Alex, this is like, I think this paper is not directly in, doing what you're doing, but it's interesting, the notation. They define for every node, like every vertex, so that would be like a primitive in the netlist they get, an m-dimensional weight vector, and that allows them to have balance constraints. And let's see, their balance constraint is here. So the balance constraint is I'm going to cut this into k parts. Okay, so if it was a 4-die system, K would be 4. And I basically, so I, if I want to perfectly cut it, I have to put 1/4 of the vertices or primitives in each one of those. You usually don't do that. You allow some imbalance. So that's what this epsilon is. So maybe this allows, if I'm set the same to a certain number, I could get like 5% imbalance is allowed. And this is just saying that they do that for every single resource. Okay, so they do have this heterogeneous balance constraint. So for the RAMs, if epsilon is 5%, you can be 5% off balanced. Or same thing for DSPs, same thing for logic blocks, etc. They also, their partitioner supports grouping constraints, and that's how they bring in these, like things that must be kept together. That's how they bring in the stuff that's pre-packed by VPR, like carry chains and so on. And their partitioner is timing driven. And so they actually hook it up to Tatum, so the timing analyzer in VTR. And what they do is they'll timing analyze the circuit with just assumed delays. And what they say they use for the assumed delays. Yeah, usually you don't know much about the delays at that point, so they probably just assume like unit delay or something
Yeah,
for
I'm
all the
wondering if
nets.
yes, I'm wondering if they're doing what the Packer used to do for like just counting. It's just it estimates that anything going between two atoms that are not part of this actually any two atoms is just some unit delay that they know, some value.
Yeah, I can't remember if they actually say that or not. In the other paper that this is building on, which is their partitioning paper, they have experiments in that which are not this. They're not about interposer-based FPGAs. But in that one, they actually hook up to OpenSTA, and they use OpenSTA's wire load model to estimate timing.
Yeah.
So they clearly can take different timing estimation functions. Okay, so
They might find AP very interesting then because I've updated the timing model to be much more accurate. So that pre-packing. So that could be interesting.
yeah, so okay, so
Hmm.
their partitioner basically has like a cost of, cuts, and its cost of a cut is this is like their equivalent of wireless cost replacement. They basically just say go through all the edges in your net list, like your hypergraph, and there's some cost alpha if it was cut. Okay, so alpha is just like a tuning parameter. It's just like a scaling factor. So that's pretty obvious, right? Just if you put terminals of this in two different partitions, you get a cut. Then they have another term, which is their timing cost. Okay, and their timing cost is interesting. So they have two pieces of it. So they have, did I cut the edge? And again, that means I put terminals on in two different partitions. And there's let's see, I got to read this again carefully. I think TE, let's see, I think T is just a weighting factor. Yeah, okay, now TE is the timing weight for that edge. So this is like coming from essentially a criticality computation that's pretty similar to VTR. Actually, might be so similar, it may have been inspired by it. So this is like timing analyze, get the slack, compute that slack ratio, and that's basically your timing criticality for an edge. Okay, so they basically weight every edge by its timing criticality, and that's their first term in the timing part of their cost function. Does that make sense? There is an interesting thing here of like you have to read the notation carefully. They have both hyper edges, and for a timing edge, really a graph you'd really like to be looking for cuts that are from source to sink. Do you know what I mean? If you cut a hyper edge, only the edges that are like only a fraction of the edges can be cut, right? Like you could have 30 terminals, you have a source, you put 15 of the destinations in one partition, none of them should get a timing hit. You put the other 14 terminals that are sinks in the other partition, those all get a timing hit. So I would assume that's how they're interpreting this, but I can't remember. I have to go and like look at their other partitioning paper to be sure. Okay, so that's basically though you have a timing criticality per edge, and you see if it's cut. and you cost that. Then they have another term, which is they extract a bunch of critical paths from the timing analyzer, and they basically cost the cuts, okay, how many times each one of these paths is cut, okay, times, let's see, TP, like times the timing weight for that path. Okay, so you got a timing weight for that path depending on how critical it is, and you're counting how many times that path is cut and weighting it by some hyperparameter gamma. So this is interesting because there's two ways to try to optimize timing. You can basically get a criticality per edge and just say watch the edges and do a penalty whenever you cut one. But you can also try to directly monitor some paths, and they're doing both. Okay, so they've got a critical path and they're going to count how many times it was cut. I don't know how much this actually buys them, but it's kind of interesting. What this allows you to do is you can actually do things like have they're not doing this, but when you're directly monitoring paths, you could do things like say one cut is okay, but two is not, right? Because one cut will still fit within the timing budget, but two cuts wouldn't fit within the timing budget. They're not doing that. They're still linear, but they do have this path-based term. Does that make sense? This actually is, I am going a little bit faster, so if there's too much, let me know. Or you guys are with me. Okay, and then this last one is probably the most tricky of all. They call this the snake factor. And in the partitioning paper, I hadn't seen this term before, so we'll maybe go off and read their partitioning paper. I think their figure for this might actually be wrong in that. The snake factor is basically trying to see for this path, right? So it's a path between a bunch of blocks that is one of the critical paths. How many times does it enter every partition? And what they're trying to look for is going to be possible to lay it out in a linear fashion on the chip, or is it going to have to double back? So even with the same number of nets cut, if the path kind of leaves some partitions and comes back into them, it implies that it's not just jiggling back and forth across, well, it basically implies like a more difficult placement, right? So that's what this snake factor is. So they put all of that into their time cost function. Are you guys mostly with me so far?
So snake factor is saying like, if you're cutting this path, it might go between two partitions repeatedly.
That's essentially what it's doing. Yeah, let's see. This is the partitioning paper. This is their partitioning paper, okay? So this is Triton Park, on which they're building. So let me get rid of this. So you see there's like a bunch of the same authors. And this goes into more detail on a bunch of the things I just talked about. Okay, so I'm just flipping through this. Like, notice there's some commonality, right? Because this is the partitioner that they're using, which is their own partitioner, so makes sense. So yeah, it's easy, like the exact same equation and so on. But this one goes through the algorithm in more detail of how the partitioner works exactly. And the partitioner has like many components. So it's kind of like almost like partitioning is a heavily studied area as well. And they almost did like a meta algorithm of like, let's take a whole bunch of good ideas from the literature and then our own, and let's just make them all play together. We'll do this and then this and then this. So it is a pretty complicated partitioner. And let's see if I can find the snake factor. Yeah, this picture, I actually think there's a bug in this figure, but this is their figure for snake factor. So it's showing a little netlist with two flip-flops and two combinational logic modules, and it's being cut into three pieces, which they call blocks, V0, V1, and V2. And they say the snake factor of this one on the left is 1, and the snake factor of the one on the right is 0. This is a critical path, like this blue line. So they're saying, well, the critical path is cut twice because it starts in V0, goes into V1, then goes into V2, and then goes into V0 again. So I guess they're saying that the number of times Yeah, that's the part that I find confusing, because to me that seems like the critical path is cut 3 times.
I think, Vaughn, it's not the number of critical times the path was cut. It's the number of
Yeah,
times you return to the same one again. So,
yeah, that's what the snake path factor is. But
Mm.
the D of P is supposed to be the number of times the critical path is cut.
Oh, right. Yeah, that's true.
So they've got both on here. Those are their two terms: number of times I cut the critical path, and then the snake factor, which is number of times I return to the same partition. And so, anyway, I understand what they're trying to do, although I do wonder if either I'm misinterpreting this figure or the figure is not quite drawn properly. So the idea of snake factor is they don't like the one on the left because you leave V0, go to V1, go to V2, come back to V0. Okay? And in the other one, you go V0, V1, V0, yeah, this is a bit weird. Okay, then I see, it's block V2. Oh, okay, they put that one in a different partition. Okay, so in this case, it never comes back to the same partition. So they could lay that out as like a linear pipeline. They put all the partitions beside each other. The first one, they couldn't lay it out as a linear pipeline because it's going to have to start at V0 and end at V0. So it's going to have to be some kind of U-shaped pipeline that's going to imply longer wiring. Does that make sense? I still don't fully understand why they called DP2 in both of those, though.
Yeah, I kind of agree. The left one would be 3 if it's the number of times you crossed. If it's the number of times you uniquely crossed, so we went from V0 to V1, V1 to V2, V2 back to V0, maybe they don't consider that one, but I do agree.
Maybe.
That would be 3.
Yeah. If they did consider that, so maybe you're right. Maybe that's the way they do it. Although that implies maybe if they'd done it the other way, they might have been able to collapse these two terms together.
Yeah.
Does DP end up in the final cost as well, or is it
Yeah, it
just
does. So DP is like the number of cuts of a critical path. So they have a whole set of critical paths. DP is one of those paths, and yeah, it does wind up in the final cost too. So where do they put it? It's up here somewhere.
it was like a sum of it, or is
Yeah, they add the two together.
it okay?
So they considered, where are they? Where is this thing?
It was pretty early on. I remember seeing it as well. It's next to this function.
Yeah, so it's here. So they have the edge-based cut weighted by timing. And then, yeah, this is the same thing we had before. Weight every path, probably again by how critical it is. Number of partitions. Let's see how they define it. Maybe they define it as the number of,
Unique, I would agree.
maybe it's just the number of partitions then. You're right.
No, it says has been cut. Yeah. Top left corner.
Number of paths. The snake, but you might be onto something though, Alex. I think you're probably right. Maybe like I'm thinking of like a cut as like you leave and you come back and count that as a cut. And they may have defined it as like a cut is, you left, like the path left or it came back, like they're treating the whole path as a unit. They're not
Yeah.
adding up the edges on the path. In which case they would need the snake factor to account for maybe I left and came back in multiple times.
Hmm.
So it's
Interesting.
interesting. I probably would have just tried to define the cut of a path differently, so I didn't need both. But I think that's a good guess of what's going on there. Let's see. So I'm actually out of time. Should I
Yeah.
stop and come back another week, or what should I do?
I think coming back another week would make sense just so we don't like have to hold people around for so long. But
Sure.
this is so interesting, actually.
Okay, that makes sense. Depending on how deeply you want to get into their partitioning flow, there's actually a lot to it, including some interesting stuff, also some things that I'm for sure going to gloss over because it's just like, okay, I read that 3 times, I got the basic idea, but that's as far as I can go.
Would you be willing to
Okay.
continue next week?
Yeah, if there's interest, so I'd be happy to keep going if there's interest.